Hi coders, JC here. Welcome to my game engine series. Today's video is about glTF and FBX loading. We are right in the middle of a mini-series about game engine basics revolving around scene and model loading. Last time we talked about scene description files and the scene graph. The next video will be about the material system and instancing. The last video of this mini-series will be about CPU thread pools and KTX for even faster loading performance. My open source game engine Lucre is based on the YouTube Vulkan series of Brendan Galea. In my videos, I'm talking about all the nitty-gritty details it takes to write a game engine from scratch. While my videos are about a Vulkan game engine, the video today is applicable to C++ game engines with any graphics API. In Lucre, I use abstract interfaces for concepts like buffers, textures, and materials. Depending on the selected graphics API, those interfaces are implemented with graphics API-specific classes. 3D file loading, however, happens on the graphics API-agnostic side of the engine. Today, I'm excited to show two modern, performant, and efficient 3D file loaders, fastgltf for glTF and glb files, and ufbx for FBX and OBJ files. With support for those file types, you have coverage of the most important 3D file formats. glTF is an open format and stands for Graphics Library Transmission Format. glb is a binary file format, while glTF files are an ASCII/JSON and human readable. Both glb and glTF files follow the same specification from the Kronos group. They both can reference external images or be self-contained by directly embedding binary data buffers. In July 2022, glTF 2.0 was released as the standard ISO IEC 12113-2022. FBX is a proprietary binary file format from Autodesk, named originally after an application called Filmbox. It is a popular 3D file format because it's universal and compatible with many 3D modeling and industry standard game engines. We will see today that glTF and FBX are powerful 3D file formats with support for scene hierarchies, elaborate materials, animation data, lights, cameras, and much more. Next to fastgltf and ufbx, I have two more loaders in my game engine Lucre, namely tinygltf and assemp. I originally started with these two loaders. Now I just keep them for reference. Fastgltf and tinygltf are quite similar. Their internal representation of the scene and model data is almost identical, only the data access is different. As the name implies, fastgltf loads glTF files faster. However, I found for glb files, both fastgltf and tinygltf have about the same performance. For FBX loading, at first, I used assemp, the loader promoted on Learn OpenGL. We will see today that ufbx, a single source file loader written in C, has a cleaner interface, a smaller footprint, and more material features. By the way, it looks like Godot is also about to introduce ufbx as an FBX loader. From all three file formats, glb, glTF, and FBX, I found glb loads the fastest. In Lucre, loading glb files is about 1.5 times faster than loading FBX files. This is because for FBX loading, we need to loop over all faces of a model, triangulate them to then generate vertices for all triangles. For a simple quad with two triangles, that would be 6 vertices per face. After all vertices are created, the index buffer needs to be set up, and the vertex buffer has to be resized for the unique 4 vertices per quad. glTF, on the other hand, can directly load the vertex and index buffers and iterate only over those vertices required. To give a future outlook, for even faster mesh loading performance, you can cache the vertex and index data. this would require an internal file format. You could save the vertex type, vertex count, and index count to disk, including the raw binary data of the vertex and index buffers. To restore the vertex and index buffers, mesh loading would come down to a memory copy. Then make mesh loading and image loading multi-threaded, and your loading performance would be way different. But that's just a future optimization and a topic for a different video. Let me introduce a few key concepts we need to understand for glTF and FBX loading. One term I will be using a lot in this video is material. The material defines the visual properties of a rendered object. It is best explained here in Blender. Blender has this material tab down here. In the shading viewport, Blender's default material node is referred to as principled BSDF. It is used to load PBR materials. PBR stands for physically based rendering. Here you can define the base color of the material, which is also sometimes referred to as diffuse color or albedo color. You can select a constant color or apply a texture. Constant colors can be specified per material or per vertex. For the latter, color values will be interpolated between adjacent vertices in the fragment shader. Then there are properties for roughness and metallicness that are used when lighting is applied to the object. You can define roughness and metallicness as constants or via textures. Here you can apply a normal map, and here you can define an emissive map for this material. The emissive color and emissive strength are configured down here. Before they are used in the post-processing stage of our engine, the emissive color and the emissive strength need to be multiplied. Blender may fold the emissive strength and the emissive color if a constant emissive color is selected before the export. When an emissive texture is provided, Blender will export the emissive strength as is, and your render engine needs to apply it in the shader. More on that later. Keep in mind that only the diffuse and the emissive textures are loaded as sRGB, while the normal and roughness metallic maps are loaded as unorm. This tells the sampler in the fragment shader whether or not to convert the color values from a texture into linear color space. One difference between glTF and FBX is that FBX requires grayscale textures for roughness and metallicness. Grayscale textures always have the same values for the three color channels red, green, and blue. So FBX needs two separate textures, while glTF can load them from a single texture from different color channels. glTF uses the red channel for ambient occlusion, green for roughness, and blue for metallicness. In Blender, when you convert from FBX to glTF, the glTF exporter converts grayscale textures to a multi-channel texture. For the other way around, from glTF to FBX, you need to separate the channels manually with GIMP. GIMP has a function called color decompose that splits an image into three layers: red, green, and blue, and you can save them individually. So material was one of the key concepts. Then there is mesh loading, whereby meshes can have multiple materials, so they are divided into submeshes. In glTF, submeshes are called mesh primitives, and in FBX, or at least in the ufbx loader, submeshes are called part meshes. If you take the simple cube here, it has 8 corners, 6 faces, and per face 2 triangles, so 12 triangles in total. Each triangle has 3 vertices, so there is 6 vertices per face, but only 4 unique vertices. Those 4 unique vertices per face we will be using in the shader. This is because each face of the cube is pointing in a different direction and requires different normal vectors. You can apply smooth shading in Blender, where the normals of vertices of adjacent faces are averaged to lower the total number of vertices. For a cube, however, all faces are perpendicular, and smooth shading wouldn't work as the angles between faces are too large. This is called flat shading. So we need 6 faces times 4 unique vertices for the model, which equals 24 unique vertices. Then we said each face has 2 triangles, so we need indices for 6 faces times 2 triangles times 3 vertices per triangle, which means 36 indices. To render different materials, we may have to use different shaders. One material may only need a simple shader without texture support, while a different material may need support for multiple textures. Per model, we create one global buffer for all unique vertices. In our example, this is an array of 24 vertices. Then we need one global index buffer per mesh to hold all 36 indices. We will only upload those 2 global buffers for vertices and indices to the GPU. Then we issue draw calls with offset vertices and indices to draw submeshes. In other words, to issue a draw call for a submesh, we need a data structure to store the offsets of the first vertex and index of the submesh. This data structure also needs to store the number of vertices and indices to be used in the draw call. This is what vertex count and index count are used for. To give an example for a single model with 2 submeshes, let's say face number 6 of our cube has a separate material. This would correspond to vertices number 20 to 23 in the global vertex buffer of the mesh. The indices for the 2 triangles of this face would be from index number 30 to 35 in the global index buffer. So we store first vertex equals 20, first index equals 30, vertex count 4, index count 6. To provide the fragment shader with material properties, we can use push constants for constant material properties, or we can bind a descriptor set for textures. Then we can issue a draw call for the submesh, only for that one face of the cube and with unique material properties. Okay, this is what you need to know about submeshes and how multiple materials per model are handled. The next key concept to understand for glTF and FBX loading is skeletal animation. When we look at the ufbx loader code today, we will encounter this topic again. There's a whole video about skeletal animation on my channel, but let me give you a quick refresher. For skeletal animation, we need to load 3 things. Number 1, the skeleton itself, which is a tree hierarchy made up of bones, where each bone can have a single parent and one or multiple child bones. This hierarchy is provided via the node graph of glTF and FBX files. For a bone, we also need to load an inverse bind matrix. The term bone and the term joint are used interchangeably. FBX is using the term bone, while glTF is using the term joint. Number 2, for each vertex, we need to load up to 4 bone indices the vertex is influenced by. So we have an array of bone transforms available in the vertex shader, and the bone indices stored for each vertex are used to index into this array. We support up to 4 bones influencing a vertex. For each vertex, we also need to load a weight that defines how strong a bone may influence a vertex. Number 3, we need to load keyframes for the animation. Each bone has a list of keyframes defining the scale, rotation and translation in the local space of a bone. That's all we need to load for skeletal animation. Then on the CPU, each frame, the local transform of each bone is calculated via an interpolation of 2 keyframes. Next, the global transform for each bone is calculated as per the formula global transform equals parent global transform times local transform. This formula requires the parent transform to be already up to date. This is why we traverse the tree hierarchy of the skeleton starting with the root and recursively. Lastly, the global transform of each bone is multiplied with its inverse bind matrix to transform the bone into model space. The resulting array of bone transforms is copied onto the GPU so that the vertex shader can do its magic. We will see in a minute how these three elements required for skeletal animation are loaded from an FBX file. Another topic relevant to glTF and FBX loading is the scene graph and how we can copy the node hierarchy of a 3D file into it. The goal here is to strip off unwanted nodes. These are mainly the bones for skeletal animation and empty nodes. For example, whether or not an empty node is copied into the scene graph is determined by its child nodes. I showed in the last video a two-pass approach. We would recursively traverse the node hierarchy down to the leaves, and on the way back up to the root, we would start marking nodes as relevant once a mesh was found. Today we will add lights and cameras to this algorithm. In a second pass, we would traverse recursively and starting with the root of the tree hierarchy again and copy nodes marked as relevant into the scene graph, parent first. Let's check out glTF. Here we see the top-level elements provided by fastgltf. These contain the data of a glTF asset that we need to load. We have a list of scenes here. glTF has multi-scene support. Scenes contain nodes, and nodes contain meshes, lights, cameras, and child nodes. Meshes may have one or several materials. Materials can have one or several textures, whereby a texture contains an image and an image sampler. In the glTF spec, the term sampler is also used in the context of animations. So there are image samplers and animation samplers, and they represent two completely different concepts. The image sampler defines how the image is sampled in the fragment shader. It defines the magnification and minification modes. For the magnification and minification modes, most of the time we use linear. However, to preserve pixel art, you need to use nearest. The sampler also defines the wrapping mode for UVs. Back to the top-level elements of a glTF file, here we have skins, which provide a node list of joints and an accessor for the inverse bind matrices. And lastly, we have accessors, buffers, and buffer views. I created a little glTF and Vulkan shrine in this scene here to give you a hint as to which of the two formats, glTF and FBX, you should start with. Here we have the grand glTF overview. It looks a bit intimidating at first, but we will see it's not that bad. Right up here, you can see the top-level elements of a glTF file listed, and we can see a graph here about their relationship. Here, the concept of scenes is explained, whereby a scene can have multiple top-level nodes, and nodes can have child nodes and a local transform. Local transform means the transform is relative to its parent. Here are the meshes and mesh primitives explained. They can have the drawing modes points, lines, and triangles. My engine Lucre only supports the mode triangles. A submesh can have a material. For the mesh itself, there are vertex attributes we need to load, such as the vertex positions and normals. Other attributes we need to load per vertex are the UVs, vertex colors, tangents, and joint indices and weights for skeletal animation. Down here it mentions morph targets. Unfortunately, my engine does not yet support morph targets. On a side note, fastgltf and ufbx do support morph targets, while asymp does not. Here is binary data explained. I will show you a template in the code to deal with that in a moment. On the right side here, materials are explained. We saw earlier in this video how the properties here relate to Blender. The base color factor always needs to be used in the shader. If the base color is provided via a texture, the base color factor needs to be multiplied with each sample from the texture, otherwise it defines the base color itself. Down here, you'll find cameras defined. Their projection can be perspective or orthographic. For a perspective camera, we need the near and far plane, the field of view, and an aspect ratio. All the way down here, we have textures. glTF uses OpenGL constants for the minification and magnification filters. To the right, we have skins and animations for skeletal animation, as discussed earlier. At the very right, GLB is explained. Fastgltf is loading both glTF and GLB for us, so we can skip this part. At the very right bottom, we have extensions. glTF files will tell you which extensions to use. Now let's check out the code. At first, we have to set up the options and extensions to be used by fastgltf. This file here, core.hpp, one of the header files of fastgltf, links to README files in the glTF GitHub repository with more details about extensions. For the options used to parse a glTF file, core.hpp provides information here. Once the glTF file is loaded and parsed, we have a glTF model that contains all the asset data. Next, we load the textures, skeletons, and materials. In the function loadTextures, we iterate over all images and create a texture for each. The image source may be provided in different formats. This can, for example, be a file name, raw memory, or a buffer view. Fastgltf provides the image source as a C++ variant. We can use the C++17 function standardVisit to handle each variant. Here we have lambda functions with arguments for different types, plus a default case if the variant type is not supported. In each lambda, we use stbi load to get a hold of the raw image data. Then we extract the minification and magnification filters. These are provided as OpenGL constants. We can pass the values directly to the constructor of the texture class. The image format is sRGB for the diffuse and emissive texture, for normal maps and roughness metallic maps, and generally for textures containing material properties, the image format is unorm. After we loaded the textures, we get a hold of the skeletons and skeletal animation data. Then we need to load the materials. Here we iterate over all materials provided by the fastgltf loader. For each material, we extract the base color factor, the diffuse and normal map, constant values for roughness and metallicness, the texture for roughness and metallicness, constant values for the emissive color and emissive strength, and the emissive texture. Back in the top level scope of the fastgltf loader, we proceed to load the nodes. After all nodes we'd like to keep are marked as such, we call the function processScene for the scene specified in the JSON description file, or for all scenes if the JSON description file didn't specify a scene. In processScene, we call the function processNodes for each top-level node of the scene. ProcessNode is a recursive function to traverse the node hierarchy of a glTF file. For each node marked as relevant, it either creates a group node, or if the node holds a light, a camera, or a mesh, it creates a game object. In the function createGameObject, the node is added to the scene graph and into the scene dictionary. Then we need to retrieve the node's transform. Fastgltf may either provide the transform via the individual components translation, rotation, and scale, or it may provide it as a mat4. Next, we load the actual mesh, light, or camera of this node. Here we check if the node holds a mesh. Only for the first instance of a mesh, we create a vertex buffer and an index buffer via the function loadVertexData. In loadVertexData, we iterate over all glTF primitives of the mesh, append vertices to the vertex buffer, append indices to the index buffer, and create the submesh structures. For each submesh, we set up first vertex and first index and the instance count, which is specified in the JSON description file. Here we create a default color for the submesh in case it doesn't have a material. Then we retrieve pointers to data buffers for vertex positions, colors, normals, tangents, UVs, joints, and joint weights. To get a hold of these pointers, we use the template loadAccessor. This template takes in the accessor, a pointer to store the start address of the data, and optionally pointers to return values for a count and a type. It returns the component type. The template retrieves the buffer and buffer view from the accessor. To get the buffer data, we use the C++17 function getIf. Then the template calculates an offset from the accessor itself and the buffer view. The stored address of the buffer plus this offset is stored in the data pointer to be returned. Back in the function loadVertexData, after we set up the pointers to the individual vertex attributes, we start to append vertices for this submesh to the global vertex buffer of the current glTF node. Here we create a vertex, and here we assign the individual fields. If no tangents were provided, we compute them manually. Next, we need to append the indices for this submesh to the global index buffer of the current glTF node. The data is provided via an accessor again, so that we can retrieve an index count and resize the global index buffer accordingly. The destination pointer here points to the first element of the newly allocated memory space. We can use fastgltf's convenience function iterate accessor with index to copy the new indices into the global index buffer. Lastly, we set up the vertex count and index count. Once we looped over all submeshes, we return to the scope of create game object, assign the materials, and submit the new model with its vertex buffer, index buffer, and submesh structures to the render engine. At this point, we have loaded the textures, materials, skeletal animation data, and submeshes. The last two things to load are lights and cameras. We are still in the scope of create game object. Instead of loading a mesh, we are loading lights here. We can load directional lights, spotlights, and point lights. For point lights, all we need to load is the intensity, a radius, and a color. Then we create a point light component and push it into the ECS. Cameras are equally simple to load. They are either orthographic or perspective. For orthographic cameras, we have to retrieve the X and Y magnifications, which describe the width and height of the viewing volume. The near and far plane values specify the extreme ends of the viewing volume in the Z direction. For perspective cameras, we also load the near and far plane values, as well as the field of view angle and the aspect ratio. For each camera type, we create a component and push it into the ECS. Let's take a look at the ufbx loader code. We're starting with the load options. The header file ufbx.h provides details about load options here. Then we can load an FBX file and set a breakpoint. Here on the left, we have the whole scene from the FBX file. We have 83 nodes and a single mesh. We have bones here and a skin deformer. If we examine the mesh a bit closer, we see here the faces, vertices, and indices. Here we have the per vertex data, positions, normals, and UVs. Apparently, it neither has tangents nor vertex colors. We are looking for a skin deformer, which is here. That means we can load a skeleton. Here we have a skin. That's our skeleton data. If we take a closer look, the count under cluster tells us the number of bones. We need to load 65 bones for this skeleton. We said we need 3 steps to load a skeletal animation. This is step 1, loading the tree hierarchy of the skeleton. We loop over all bones to set up a map that converts from bone names to bone indices. Down here, I added a little helper lambda to convert an FBX mat4 to a GLM mat4. Here we have another lambda that can be used to traverse the node hierarchy of an FBX scene. The lambda takes in a node of the FBX scene hierarchy and a parent node. In this lambda, we check if we can find the name of the node in the conversion map. If so, it must be a bone, and we add it to our internal skeleton, including its inverse bind matrix and its parent. Next, we iterate over its children. If the current node is a bone, and if the child node is also a bone, we add the child to our internal bone structure. Then the lambda calls itself recursively for each child. Then back in our main code, we call this lambda with the root node of the FBX scene and with no parent. Step 2, loading keyframes. We will store the keyframes in the same structures that we use for glTF. So we get the number of animations and loop over all of them. For each animation, we store the time of the first and last keyframe here. Then we use this here ufbx convenience function to obtain a pointer to a baked animation. Here we have two more helper lambdas to convert a vec3 and a quaternion to glm. Then we can loop over all nodes of the baked animation. If the name of the node can be found in our conversion map, it is a bone, and we can set up animation channels for translation, rotation, and scale. We enumerate the sampler indices starting with 0. The animation samplers of our internal representation hold the keyframes. So we get the number of keyframes, resize the arrays for the timestamps and transform components, and set up the interpolation mode. Then for each keyframe, we store the translation, rotation, and scale. We push the animation into our animations array. If an animation was found, we set a flag accordingly. And that's it for step number 2. Step 3 is to load the bone indices and bone weights per vertex. This happens in the function load vertex data. We'll get to this in a minute, because before we load the vertices, we have to load the materials. Back in the main scope of the FBX loader, we proceed with loading the materials for all meshes in the FBX scene. The materials can be found directly at the top level of the FBX scene structure. We retrieve the number of materials. Then for each material, we retrieve the base color, roughness, metallicness, normal map, emissive color, and emissive factor. Isn't the code neat? The load material function is equally clean. It is one big switch statement that for a given material property retrieves a ufbx material map. If the map holds a value, it checks if a texture is available. If so, it loads the image. Otherwise, it loads a constant value. Here for the diffuse color, it also extracts the base color factor that is multiplied in the shader with the samples of the diffuse map. Here for the roughness, the code is a bit simpler. To load the image, we retrieve the file name. In load image, we check if the file exists, and if not, we try again by adding the relative path to the file name. If the image was loaded, we set up the texture index in the material and push the texture into a global array. Once we loaded the materials, we return to the main scope of the ufbx loader. At first, we're marking nodes in the scene hierarchy as relevant. Then we traverse the scene hierarchy again to load the meshes of each node. In process node, we set up the node's name that will be used in the scene graph. If the node was marked as relevant, and if it has a mesh with triangles, we create a game object. In the function createGameObject, we insert the node into the scene graph and load its transform. The transform is provided as translation, rotation, and scale. For the first node under the root node, I'm adjusting the scale and translation by a factor 100. I tried to do this with the load options of ufbx, but couldn't quite figure it out. If you know how to do this, please let me know in the comments. Then for the first instance, we proceed to load the vertices. We get the number of submeshes and load each submesh individually. We set up the first vertex, first index, and instance count of our internal submesh representation. Here, we set up a default base color in case the mesh doesn't have a material. Then we need to load the vertices. We need to check once if the mesh has tangents, UVs, vertex colors, and a skin. If we find a skin, we can load bone indices and bone weights for each vertex. Vertex positions and normals are guaranteed to be there. Now things get different compared to glTF loading. For FBX, we have to loop over the faces of the submesh. We get the maximum number of indices per face and allocate a temporary buffer for vertex indices accordingly. Then ufbx provides a helper function triangulate face. It fills the temporary buffer with vertex indices for all triangles of a face. Then we can start to create vertices by looping over all vertex indices for all triangles of the current face. So per vertex, we set up the positions, normals, tangents, UVs, and vertex colors. For vertex colors, we need to convert the color space from sRGB to linear. This is at least the case if you use in Blender the default export options for FBX. If the node has a skin, we loop over the bone indices and weights. The weights need to be normalized, which happens here. Then we can append the new vertex to the global vertex buffer. Once we loaded the vertices for all triangles of the submesh, we need to append indices for unique vertices to the global index buffer. Here we get the number of all vertices created so far for this submesh. ufbx provides a helper function called generate indices. It rearranges the vertex buffer to only contain unique vertices and fills an index buffer accordingly. It takes in a ufbx stream, which has a data pointer, vertex count, and vertex size. This ufbx stream is created here. We also need to allocate space for the new indices to be appended to the index buffer. After we rearranged the vertex buffer from 6 vertices per quad to 4 unique vertices, we can downsize the vertex buffer accordingly. Then we store the vertex count and index count in our internal submesh representation. Now the submesh is loaded. We return to the scope of Create Game Object, assign the materials, and submit the newly created model with its vertex buffer, index buffer, and submesh structures to the render engine. That's it for today, guys. Thanks for watching. Please like this video and my engine on GitHub. If you'd like to see more videos like this one, please consider subscribing. See you next time. Bye bye.